Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started today, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on cost-effective remediation through enhanced characterization. With that, I'd like to introduce our presenters for today. We are pleased to have with us Richard Desrosiers, Associate Principal and Hydrogeologist at GZA GeoEnvironmental. Mr. Desrosiers is a licensed environmental professional in Connecticut and a licensed professional geologist in New Hampshire and Tennessee. His 33 years of environmental experience have focused on understanding complex geology, hydrogeology, and geochemistry associated with soil and groundwater contamination. His responsibilities have included utilizing state-of-the-art investigation techniques, including high-resolution site characterization, RCRA and CERCLA hazardous waste investigations and closures, and the development of innovative in-situ technologies to remediate groundwater contamination. Mr. Desrosiers is actively involved with multiple interstate technology and regulatory council teams, including optimization of in-situ remediation and injection strategies, and PFAS. We're also pleased to have with us today Maureen Dooley, Director of Strategic Projects at Regenesis. Maureen has more than 25 years of experience in the remediation industry. In her current role at Regenesis, she provides technical leadership for complex soil and groundwater remediation projects throughout North America, as well as remediation design, strategy, and business development in the northeastern United States and eastern Canada. All right, that concludes our introduction. So now I'll hand things over to Maureen to get us started.
Hi, and thank you, Dane, and happy holidays, everyone, and thank you for joining, and welcome from the lovely GZA office in Glastonbury, Connecticut. I also want to thank Rich for putting together this presentation. There's a considerable amount of time and effort that's involved with one of these, so Rich, thank you. Now, Rich and I have known each other for a long time as we've been knocking around this industry for a few years together. And Rich is someone who's very thorough, a great geologist, and has always had an eye towards innovation. Now, with the presentation today, it's a big site. It's a complicated site. And I think when you see the slides, every slide just has a tremendous amount of content, and it's really a testament to GZA and the work that they've done on this project. Now, for Regenesis and for me as a remediation practitioner, sometimes getting involved with some of these sites can be quite daunting. But with these enhanced site characterization techniques that have been employed at this project, it's really allowed us to be a lot more focused in our approach. But another comment I want to make is, you know, sometimes when I've been in presentations at conferences and I say, oh, enhanced, you know, remediation or all of these enhanced techniques, these are for the large, big budget sites, and wait a minute. But I think you're going to be really pleasantly surprised with this presentation to see there are a lot of techniques that will be presented here that will be applicable to, you know, really projects of all sizes. So really with the stated goal of trying to develop a focused, objective, and a focused approach that ultimately is going to provide a cost-effective remedial solution. So with that, Rich, I'm going to turn it over to you.
Thank you, Maureen, and good afternoon, everybody, and thanks for joining. And I'd also like to thank Regenesis for hosting this webinar today. So as Maureen indicated, while this is a large, complex site, these techniques can be used on smaller and have been used on smaller sites. So with that, I'd like to get going in terms of how using enhanced site characterization can provide cost-effective remedies. This is a site in terms of the outline that we'll be doing. It is basically looking at regional deposition, some subsurface characterization, groundwater flow. There's an interesting geochemical cocktail that comes with this site. We did some pilot studies to enhance our injection design, and we'll look at some of the data results. Just real quickly, just giving a general mile-high overview, this site is located in the northeast within the old glacial Lake Hitchcock deposit of the Wisconsin-era glaciation. As you can see on this LiDAR map, we're located in a distal delta into the east of one of the deltas in terms of the glacial lake that was formed. The blue are the lake bottoms, so you can see we're very close to the lake bottom deposits. One thing that really influenced the deposition was the glacial outflow and the meltwater itself. As you can see in this picture, we have a stream here where we will find out later on that the plume actually migrates beneath and actually discharges it to this northern tributary. The green is a glacial till, and working with USGS Byron Stone, he identified this as an Illinoisan age glacial deposit versus the Wisconsin age deposits which we're working in. So that influenced the hydraulics significantly in terms of fate and transport. Where are we within the delta? Obviously, we're in the distal end of the delta itself. So what we see in this cross-section of the deltaic deposits, the yellow are the sands, the blue are the clays, and that's really what we're in. We're in this interfiguring or facies change within the deposit itself, and those are unique to this particular site, making it very difficult to characterize. The site itself, as you can see, looking at this topography, the highlands is where the site is located and where the bulk of the investigations occurred. However, as you can see from the topography where the dark black areas are, very steep slopes, almost 30 to 40 foot change in elevation down to the wetlands and to the surface water deposits. In the lower right corner where the stream is located, that's also the glacial lake bottom deposits. What we saw is that through the investigations, we found a hydraulic divide that ran through the site. We had a couple of releases, one a chlorinated solvent release, and a second being a hexavalent chromium release. Because of the complexity of the geology, what we ended up with is a series of 3 plumes that discharge in 3 different directions from the VOC release, and 2 plumes that discharge from the chrome release. We'll be predominantly talking about the chrome release as well as the VOC release that goes to the northeast. The site itself is approximately 700 acres of investigations that we looked at. So looking at it differently, we can also look at it on a shaded relief. And again, you can see the upland area being in the center and the deeper deposits which influence the migration shows up fairly well on this type of a map. So as we proceeded, we looked at a lot of different drilling methods. Those drilling methods are listed here, and I'm not going to list them all. But you can see we use a large number of methodologies in order to try to characterize the site. What we found is there was a number of drilling issues. First of all, we found some drillings that ended up with poor resolution, that is, low recovery. Auger split spoon samples were not very good and missed a lot of the geology. 5-foot direct push, we had issues with some of those in terms of the silts and clays clogging the sampler. Drive and wash, we found that it had some good recovery, but it was slow and introduced water to the formation. Some of the better resolutions that we saw were with dual rotary. However, with that, we were collecting the samples through a cyclone, so it wasn't as depth specific as we would have liked. Rotosonic was very good with good recovery. We did have some disturbance in the extruded, but we did see things like chevron folds and other things, features within the core samples. And 2-foot direct push samples were much better than the 5-foot direct push samples. In the rotosonic, one of the things we did find, which was actually very important to the site characterization, was a drop stone at about 90 feet below grade within the lacustrine deposit. This drop stone, measuring about 4 inches in length, was actually embedded within a clay deposit at the bottom, which ended up being the lower boundary condition on the site from a vertical migration of the contaminant. The high resolution soil profiling worked out extremely well, where we got 1/10 of a foot resolution using either the membrane interface probe or the Waterloo profiling. However, the limitation of that was about 100 feet. So as we looked at how the high resolution site characterization was used, on the left side of the figure is really an indexing of hydraulic conductivity using a Waterloo profile. On the right was potentiometric surface. So the orange arrows show a downward vertical flow and the blue showing an upward vertical flow. Coincidentally, where the two flows converged was our contaminant zone. This was really in the upper portion of the site at about elevation 160 to 170. In the lower discharge areas at elevation 130 to 140, we found that a lot of the upper geologic units were eroded away. We see that the discharge is much shallower, where we have upward vertical flow, generally from 25 to 90 feet below grade, and shallower downward flow from 0 to 25 feet. Again, we found that the contaminant was migrating within that hydrologic zone. When we look at trying to compare the data of the high resolution site characterization to corings that we collected, we had some interesting correlations. So the black line on the left represents the indice of hydraulic represents the soil profile. So in this particular case, the soil profile with the black as it goes further to the right are silts and clays, and the profile going to the left are sandier units. So this is an MIP profile. The red represents the PID, or the contaminant profile. A couple things that come of interest at the 120-foot zone, where we see a couple of peaks of red where their chlorinated solvents are present. We also see they correspond very well with the sandier unit bounded by a silty or sand or clay unit. As we go down further into the profile, we see that the PID hits are predominantly on the silts and clays, and not so much in the upper profile. And that's consistent down at 106 feet. And as we go down lower in the 100 to 95-foot area, we see a higher concentration of the PID, and then it quickly diminishes. At around 95 to 100, further to the east of the site, are also the locations of where the lake bottom deposits are. So that gave us some indication in terms of how deep the contaminant might have migrated. And you can see in the center core, we have how that represents in terms of the PID values that we hit within the soil. So you can see there is some changes in the vertical contaminant profile, and those changes are fairly consistent with what we're seeing in the profile itself. Some of the things that we found unique to the site, because it was in the distal delta, and also because Lake Hitchcock varied in its height over seasonal variations, we found a number of desiccated clays. Those became important in terms of how contaminant migrates through the lithology on the site. The other important thing on the site is really the heterogeneities. Because we have very fine units, we start seeing that well placement becomes critical in terms of how we need to identify where the total mass may be present. So we see we have two samples that we collected. Both the midpoints on these samples are identical. So we have a 2-foot screen that shows TCA at 2400 and a 5-foot screen that shows TCE at 677. The difference here is that the profile on the 5-foot is extending over this upper small deltaic hydrostratigraphic unit and this lower one, where this one was more predominantly right within this zone, probably where the higher concentration was present. Again, we see a similar profile in terms of using a 2-foot and a 5-foot for TCE concentrations. Again, we see that the 5-foot profile tended to be more accurate. And again, you can see that we have these silty clay units, probably where a lot of the contamination is residing within this unit, where the shallower 2-foot is in the upper portion with the lower concentrations. So again, looking at this is very critical in terms of well placement in order to understand how much mass is present for the stoichiometric calculation required to augment the site with an additive to be successful at the remedy. Other things we looked at the site, in addition to the VOCs, was also to look at how the hexavalent chromium profile might look. We used basically field hatch kits looking at hexavalent chromium, collecting some soil sample, mixing it with DI water, creating a solution, and then basically filtering that solution and then putting a packet for evaluating colorimetric for hexavalent chrome. The darker pink is much higher concentrations of chrome, where the lighter pinks are lower. So you can see we were using this in order to identify vertical stratigraphic sequence and tops and bottoms of where the hexavalent chrome was. And then we can apply those data to a vertical profile, looking at both PID and hexavalent chrome, to be able to start estimating what is the thickness of the treatment zone, in this case, a 4-foot zone. So again, we're finding that these zones are very narrow, and again, the strategy for our remedy for the site. This was a profile through the chlorinated solvent plume. This became a real interesting profile for high resolution site characterization. We clearly identified some fairly high chlorinated solvent concentrations up to almost 6,000 ppb, with a lower boundary condition just below that. We went out with the high resolution, which you can see here in the blue. Those are the MIP profiles with the silts and clays to the right on the profile and the sands to the left. We then took that profile and then evaluated the lithology. So the darker colors are the silts and clays, where the lighter colors are the sand. So again, we clearly see that the upper unit bounded by the yellows, which are a clay unit, are really where the contaminant is. And again, the conceptual site model is showing that the contaminant below the clay unit represents a boundary unit in this conceptual site model. However, when we went out and we conducted high resolution site characterization just prior to an injection program in that upper zone, we identified a large concentration of chlorinated solvents directly below the lower clay unit. So as you can see, we identified also that there was a vertical upward flow within that lower formation. This was also connected up to the release zone, but in this particular application, this thin layer of high concentrations of chlorinated solvents was actually below a thin clay unit. So our original treatment zone would have missed that lower contaminant if it wasn't for the addition of the high resolution site characterization. So we went back out and we collected some more groundwater samples. And as you can see, the concentrations varied from low concentrations to the right of the profile to upwards of almost 6,200 parts per billion within the high concentrations identified with the PID. So because of this high resolution site characterization investigation, we still confirm that the conceptual site model for that particular well screen still made sense. However, the final treatment zone was extended a couple of feet in order to target this lower contaminant zone identified through the high resolution characterization. What this meant for the client is that we didn't have to remobilize a second time. We didn't have to reevaluate why rebound was occurring because we had not identified this lower contaminant zone. There was an incremental cost to the drilling as well as an incremental cost to additional chemical oxidant in order to treat this lower zone. So with this methodology, we were able to save cost in terms of this injection program, and we were able to remobilize within a month after the collection of the data. The importance of heterogeneity also came out on this site in terms of well placement. These are two wells, and refer to them on site as MW11 cluster well. The one to the left was installed previously prior to evaluating the lacustrine deposit, and we found that the concentration was 180 parts per billion. To the right, we've installed a deeper one to the top of the lacustrine. So you can see the wells are located, one in this upper lobe with lower concentrations and two in this lower lobe with higher concentrations. Again, these lobes are only 3 to 5 feet thick. So when we come to looking at boring logs, this is a typical log that we would normally go out and install with a monitoring well. We do good jobs in terms of describing the lithology, adding in PIDs in terms of where we have hits within the profile itself. On this particular site, we actually measured PIDs every 6 inches due to changes in lithology. Ended up being very valuable in terms of the remedy. But sometimes if you take a traditional boring log and convert it to an XL log, and then take each individual layer, and then you can extract a lot more information versus a typical boring log. So in this particular application, this is the same boring log as if it was done on a traditional boring log form. However, you can take that same boring log and start coloring it in terms of permeable units, such as the sands are in yellow, the silts are in green, and the clays are in the reddish color. And what we find is that as we go down, we can then add in our PID and chrome data. So we can clearly see that the chrome is predominantly being transmitted within these more permeable sand units down to this clay unit, approximately 20 inches below. And then the chlorinated solvents go a little deeper. So with that, we were able to target this specific zone, knowing where to inject, and this contaminant zone was 6.5 feet. We also had the ability of identifying where the top of the faucet bed was, which added into how contaminant were migrating on site. So we have the release zones, and as you can see, we have high points in the brighter colors. These other colors are areas where contaminants could migrate deeper in the profile, and including this deeper zone in the center portion. We add that into looking at how groundwater flows on site, and this is the water table, and you can see how this glacial drumlin really influences in terms of where the hydraulic divide goes, and how groundwater flows both to the north, to the south, and to the east. Looking on top of the lacustrine deposit at around 70 to 80 feet below grade, we can see that the drumlin also has an influence on that, and changes in flow directions generally correspond with the water table. And also we see that below the lacustrine deposit, we have a different groundwater flow. So looking at the groundwater in the shallow up to the lacustrine, we see that we have local discharges to adjacent streams, whereas the deeper profile, we have more regional flow. That was also very important in terms that the deeper profile or the deeper groundwater was not contaminated, so the lacustrine deposit acted as a boundary condition. We then also looked at how the contaminant was migrating vertically within the profile itself, and we put together a hydraulic flow net. And in the release area, we had very strong vertical downward flows up to 1/2 foot per foot. However, at the top of the lacustrine, we were near 0 vertical flow, and the contaminant was then migrating from the release zone, and then we had an upper vertical discharge to the discharge zones. Looking at it in profile, a couple really important things came into play in terms of the final remedy. We have the contaminant has migrated deep within the profile itself. These profiles are either MIP profiles or Waterloo profiles, along with geologic interpretation of borings that were also evaluated to create the cross-section. The red unit is the lower lacustrine deposit. The red is the chrome migrating through the silts and the clays or the deltaic deposits. What we see in the brook area, we see the contamination flowing beneath the brook and heading out towards the tributary, as mentioned earlier. However, the important thing is that these upper units were incised by the glacial meltwater. The incision of these upper silts and clay units allowed for rapid recharge into the lower sandier deltaic deposits. This in turn resulted in the plume naturally attenuating and resulting in non-detects within the plume itself. So this was an approach in terms of the natural remedy of mass reduction within the plume with natural attenuation at the discharge zones. We also have a section we'll look at next at the discharge. So we can see that the chrome concentrations are in yellow. These are groundwater. And we see the profiles as well. We can see that the lacustrine clay deposits at the bottom, and we have the sand deposits intermixed with silts and clays. In the center, we have the core of the contamination. We're bounded both to the east and to the west. And we have a unique layer here, which keeps most of the contamination. Here's a non-detect at 135. The same over here, we have higher concentrations, but lower. In the center core of the plume, we have higher concentrations. So again, we identified a 15-foot thick zone as to the down gradient plume, and we have wells appropriately installed within that discharge area so we can monitor the down gradient effects of the treatment. The discharge itself was related to a metal finish process line with a series of acids and a degreaser for the chlorinated solvents. Of course, the best location to put a metal finishing and a degreaser is along a hydraulic divide, which we'll find out bifurcated a plume. When we look at the adjacent cross sections, we can start seeing how the chemistry or the contaminant migrated deeper through the upper foreset beds and then came to a point where the green are the chrome field screening in parts per million, and the yellow are the groundwater concentration. So you can see right in the center here, we had the area where the contamination was migrating downward. One thing that we didn't see in this particular figure is that these are low concentrations. However, we did an initial pilot in this area, and those concentrations were in the 4,000 parts per billion range. The other section shows similar concentrations where we have the profile within the soil concentrations and the hexavalent chrome, both with field kit as well as laboratory analyses, allowing the contamination to migrate into these lower, sandier, siltier units. And again, over to the right where the initial pilot was conducted to reduce concentrations. As I told you, the site release was acids. However, the geology decided to change the geochemistry of the release. So you can see in the upper profile above the first silt unit or within the foreset beds, our aquifer was pretty acidic, somewhere in the almost 4.5 to 6.5 pH. However, as the downward vertical flow, as I mentioned, we had a 0.5 foot per foot in some of the upper deltaic sequences. The pH changed to be more basic, approaching a 9 pH unit. This was predominant within the plume itself, having a pH of 8.5 to 9.5. Obviously, we're trying to convert hexavalent chromium to trivalent chromium. And as we look at that, there are two ways that we can do that. We can adjust the pH, or we can adjust the EH. So within the plume, we had fairly stable hexavalent chrome, where we had our pH at around 9 and our ORP up around 0.4 EH units. And with outside the plume, we were fairly stable, and we didn't have any chrome concentrations within the groundwater, so we had stable chrome outside the plume. Other parameters that gave us a little bit of headache, besides having high concentrations of hexavalent chrome up to 38 parts per million, our dissolved oxygen was very high, up to 8.6. We had nitrate levels that we knew that we were going to have to deal with if we were going to try to convert things in situ. We also had high sulfate concentrations, again, pH, a maximum of 9.5. And we had very high oxidized groundwater, probably due to the release being oxidizers themselves at 550 millivolts. And unfortunately, we had a very sterile environment, so bio was something that we didn't think was viable. The other issue we had within the chlorinated solvent plumes is we didn't see any real degradation products within the plume until we actually got to the discharge zones. So we looked at whether it was abiotic or biotic degradation. So we converted our concentrations along the center line of the plume into millivolts. And what we found is that within the plume on site, within the deltaic deposits, it was predominantly abiotic. And then once we got into the area where the glacial meltwater eroded the upper sediments, we got into biotic degradation and natural degradation of the contaminant. So the pilot I mentioned earlier, we wanted to look at, would it be effective to take a small area and to inject some products to see what was successful. So we looked at dextrose, HRC, 3-DME, molasses, and some EDC, and we found that the HRC and 3-DME seemed to be more successful in a bench scale pilot. We injected 6 points around 3 cluster wells, and we monitored this very rigorously to evaluate field parameters such as pH, conductivity, ORP, temperature, to evaluate how far out the injected material would have gone. So we assumed that we could get a 17-foot effective radius in a 12-foot zone by, injecting approximately 600 gallons per point, or 4 to 6% of the volume of the aquifer. We found that in this particular application, most of the injected material really fell out between 12 and 15 feet. We did the injection in 2018, and we monitored it for 10 years. And actually, after 8 years, we still saw methanogenesis within the monitoring wells within the pilot area. And the results itself, we saw that after 40 weeks, we converted the hexavalent chrome to chrome oxide. The pH, as you see on top, dropped a little bit, but went right back up. So again, the pH was a major concern that we had to adjust the ORP within the formation, that the pH is sort of stable within the environment itself. So in order to make this work in situ, the pH is something that we couldn't count on, so we needed to change the oxidation of the formation itself. And like I said, methanogenesis was observed after 8 years. So we look at the plume again, like I mentioned, we have the release, and being on a hydraulic divide, it bifurcated very nicely into 2 directions, one to the northeast, and the other one to the southeast. But due to the high resolution site characterization, we were able to really come in and look at trying to profile how groundwater migrates, and then also look at the rate of migration or seepage velocity. So we were able to develop a very good groundwater flow direction, both within these 2 lobes from a central release. And then overlying the plume itself, you can see how it respects the groundwater plume in terms of groundwater flow. And you can see this one flows in this lower deltaic lobe, where this one's going to the north, as I mentioned, into the deeper location within the northern tributary, and flows underneath the stream here. And of interest, we actually collected samples up in this northern tributary, and we found that the peat unit was probably in excess of 4 feet. We did find some chrome at around 36 inches below grade, but no chrome ever made it to the surface. So that was really important in terms of the identifying the natural attenuation within the discharge area. So the design itself was really based upon 2 things. One, looking at the plume concentration itself. As I mentioned, where that well placement was important was this location right here. That's where the MW11 well cluster was. And you can also see it's also the location of the highest concentration, and this what we refer to as the core portion of the plume. We also then looked at, well, what is the mass? Concentrations are one thing, but we really need to look at the stoichiometric calculations for the additive based upon the mass of the contaminant that's actually present. So we looked at that also based upon the formation itself. So because we were able to finely tune the characterization, we were able to develop a contour map of the upper portion of the contaminant zone. So this really shows the top of where the contamination is. Then we were able to develop the bottom. In other words, how deep did the contamination go? And again, you can start seeing how, this one little core area sort of corresponds where the total mass was located, where the high concentrations were located, also where MW11 cluster was located, and how the approach of injecting within very specific areas within this zone. So we developed the injection points, which are the X's, within the plume itself, and this is just the thickness contour of the plume. So here you can see that we're up to 15 feet depth of the plume in this location, based upon a change in elevations. So this is really where the core of the mass and the core of the concentration was, and we injected within this area, along with basically 5 different barrier walls, rather than trying to inject everywhere within the plume. Became a cost-saving strategy for this particular application. What we found is that we had a seepage velocity of 35 feet per year. So that means, based upon our pilot, if any water moving through one of these barriers would be effective for 280 feet over the course of that time. We looked at the distance between each of these barriers. So the distance between this group of 3 injection points and this group of 3 injection points was 80 feet. So we really wanted to not look at the total maximum area, but what would be effective if contamination from here moved through these barriers and was remedied and then continue to move through. We used a solution of sodium lactate to sort of augment the formation to get general reductions within the formation itself. We used the 3DME, which was the polymer from Regenesis, to add for the long sustained activations that we saw in the pilot for 8 years. And then we mixed all that with water. We looked at this particular area as the core. We injected 81,000 gallons. Up near the release, we injected another 73,000 gallons. So the total area treated was approximately 5 acres using 155 points. We injected from the bottom to the top using a 1-foot injection probe. The thickness was approximately 10 to 15 feet in the core area and up to 29 feet near the release area. These were our flow rates and pressures that we used. But the really important takeaway here is that if we decided to go with a traditional injection based upon injecting 30 feet on center, the 5 acres would require 1,230 points, or almost 8 times the number of points, versus this strategy of coming in and using sort of barrier walls, allowing the natural migration of groundwater to flow through these to be effective in the treatment to reduce total mass. So here's a couple of fun slides that we do in the field during our injections that make a lot of sense in terms of validating our conceptual site model. So we look at, when we're driving the injection points, field staff measures how many seconds per foot to drive the points in. So this is a representation of 2 feet of drive rates from the top of the formation to where we inject it to the bottom. So the light color blues are less dense, the more permeable units, where the darker blue, yellow, and oranges are the more dense units. So with this, we should be able to see whether or not the contamination is sitting within these more permeable units. So as we go down in profile, we can start seeing the validity of our conceptual site model where the mass was the highest, and we can see how the geology changes, and if we have to come back and do additional investigations or injections, where we want to put them and where we want to try to avoid. So here's the plume prior to any injections with the maximum historic concentrations. What we see is that the plume goes to the northeast, This is the current post-injection of the plume. And we can see that from a color standpoint, there's a dramatic change in concentrations that were up in the 6,000 in the core and almost, 17,000 to 38,000 in the release area. What we found in the post-injection data is that in the release zone, we saw the hexavalent chromium was reduced by 92% for all concentrations within that area. We're still looking at the mass calculations, which we'll be providing to the client after our reassessment. But the maximum concentration went from 38 parts per million to 8 parts per billion. In the core area, we saw an 80% reduction in concentration. In the downgradient area, which was not influenced by the injection directly, because not enough time would have allowed to have the contamination move down that way, but we still saw a 53% reduction. In the eastern lobe, again, we saw very similar types of things where we had the core concentrations, which were dramatically reduced after the injection. We noticed similar types of concentration releases within the release zone after 24 months of 92%. Down gradient, again, outside the injection zone at 50%, and further downstream, again, these are more in the distal delta, so finer grain materials at 30%. In the chlorinated solvent plume, I'm not going to spend a lot of time on this, but again, very similar lithology, deltaic sequence. The green is where the TCE was, and as you can see to the right, again, natural attenuation through recharge as a result of removing the upper soil profile during the glaciation. Again, here's the maximum TCE concentration of that particular plume. After the injections for ISCO, we see these are the current TCE concentrations, which are significantly lower in concentration. What we found is that through the use of persulfox in the release zone, we had an 82% reduction in concentrations. This one well that had 9,400 that we identified with high resolution is now at 672. In the core zone, where we use Regenox, and Regenox was chosen because this was done significantly earlier and before the persulfox was really on the market. We saw a 61% reduction in the core, and more significantly, much further down gradient, approximately 1,000 to 1,200 feet down gradient, we still saw a 52% reduction just by reducing the mass within the core of the plume. So we drop the mass in the core, we shrink the plume, we have down gradient reductions. So cost savings, where do we see cost savings? Initially, the project was looking at a pump and treat for about $6.7 million using hydraulic control. We had to do upgrades through on-site wastewater treatment, long-term O&M, and we had to discharge that groundwater. Using high-resolution site characterization, we drastically reduced uncertainty. We were able to come up with a regulatory criteria of mass reduction that was accepted. We also had done an ecological risk assessment that it didn't identify any probable risk down to the wetlands, further supporting mass treatment. There's a technical impracticability issue with back diffusion, long-term M&A with a $2.7 million cost, or a $4 million savings by really understanding and reducing uncertainty and going in with in-situ treatment. One of the ITRC slides that can be looked at in terms of the effectiveness of enhanced characterization. So this is remedial design characterization in blue. So there's a cost increase, but you can see in terms of the rate of return, that cost increase is very effective in terms of reducing the time of the remedy as well as the cost of the remedy. So the benefits that we found in terms of looking at this site, clearly understanding the lithology, the geology, the groundwater flow, the hydrogeologic factors and geochemistry, really reduce the uncertainty by really improving the conceptual site model to basically we much further delineated the vertical and horizontal nature of the extent of the contaminants, thereby providing us the ability to strategically target these contaminant zones to reduce the amount of additive and time necessary to inject. So that led to a much more cost-effective remedy. by identifying the down gradient geologic conditions that resulted in natural attenuation prior to discharge, allowed us to come up with a focused mass reduction within the core of the plume, followed by an M&A, rather than treating the entire 2,500 to 4,500 linear foot plumes. That would have been cost prohibitive. This provided a very reasonable approach to reduce the mass within the core, shrinking the mass, resulting in concentrations decreased down gradient. That resulted in a significant cost savings to the client. Both ISCO and ISCRA were very effective when specifically targeting the contaminant within these unique hydrostratigraphic units, remembering that these units were anywhere from 15 to 5 feet thick. And I would argue that these incidental cost characterization costs are more than outweighed by the remediation cost savings. In other words, your cost savings on the remediation through the understanding of these characterization costs is really something that I think either on a large site or a small site should really be considered. And with that, we'd like to take some questions.
All right, thank you very much, Rich. That concludes the formal section of our presentation. And so at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a few reminders. First, you'll receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, after the webinar, you'll receive a link to the recording as soon as it is available. All right, so let's circle back to the questions. First question is, what program or programs were used to create the cross-sections?
Excellent question. The program that I used was Surfer, and uniquely adjusting Surfer, instead of looking at it as a 2D contouring package, looking at it as a 3D contouring package, and allowing me to connect the various lithologies based upon soil boring data along with the high resolution profiles.
Okay. This next question is a little bit long, so please bear with me and let me know if you want any portion of it repeated. Here's the question. Given the volume of amendments ejected into the subsurface, how did you determine that the reduction in COC concentrations was due to the destruction or conversion of the COC, and how much due to the dilution and or displacement from the treatment zone caused by the injected fluids?
That's a great question. A couple things that we did was to understand how we could move plumes through injections. And therefore, we did our injections in the cleaner fringe zone of the plume, working our way towards the center. We also had a number of monitoring wells that were both outside and inside the plume. So while we did have a large volume of water that was injected within the plumes themselves, we were able to evaluate that the injected material through field screening was actually observed within the areas of where we were monitoring. So we believe that most of the destruction observed within the chlorinated solvent plume was due to the additive injected, either the Persulfox or the Regenox.
Okay, great. So next question is, how long did the investigations take and how much did they cost?
That's always a good question. I don't think my client's going to let me say how much it cost, but how long it took. We were probably, prior to, this was actually being investigated previously by other entities for approximately 12 years. Their conceptual site model retained all the contamination within the 85-acre footprint of the property. Once we got involved, we spent another 2 to 3 years doing investigations. We then further characterized the 700 acres during that period of time, including these high-resolution characterization techniques, as well as really applying the understanding of the regional geology and depositional events that occurred in order to understand where the contamination could have gone. And for instance, during our first investigation, there were no borings that were done beyond the 85 acres. We went 2,000 feet down gradient. Within one of the chlorinated solvent plumes, we found 4,000 parts per billion within the first boring, based upon the depositional characteristics of where we anticipated the geology and the migration of the contaminant.
All right. So next question is, have you projected the time to remedial completion from the initial injection, or are you performing sequential multiple injections?
In the chlorinated solvents, we have done multiple injections. However, the predominant area of the multiple injections is related to really where the contaminants had sorbed for over 60 years within the site. So those areas are also being reevaluated in terms of back diffusion and how best to treat those perhaps differently. In terms of how long we have projected this particular site for M&A out to somewhere between 2040 and 2041.
Okay, great. So next question here is, did you monitor CVOC degradation products, and what were those findings?
Do we get any? I don't think we have many degradation products, in the chrome when we had.
Yeah, in the VOC areas, we saw really no degradation process.
Yeah, that was an oxidation process, so we wouldn't expect to see any DCE vinyl, and we did not observe any, as I recall.
Yeah.
And I'm trying to recall, was there in the pilot zone with the hex chrome? It was, the thing is, with this particular formation, there just wasn't a lot of natural degradation taking place. The pH was 9. That's why we were really looking at abiotic processes for this, and bioremediation was really just not part of it. And with the ISCO, because with our ability to get the reagents delivered, we believe we had a really good likelihood of getting some significant reductions, which I think bore out with some of the data that we saw. I don't know if you agree,
right. We saw really, even in the chrome area where we used, different product, where we used the ISCRA versus the ISCO, we really saw no degradation of the chlorinated solvents. And really the only place that we saw any changes in degradation were really near the wetland and discharge zone. And because of the volume of surface water infiltration, that rapidly diminished, and we didn't see that get to the surface water bodies themselves.
One thing, Rich, I'm just looking at a question. It's not one I flagged for you, Dane. Just for some clarification, there were zones where we used 3DME for reductive, and that was for really chrome only.
Yes.
And then there were other areas that were separated that were for TCE, and that was ISCO only. So I think there may be some confusion with people. We were using ISCO. It was not in the area where we had hex chrome.
That's correct. The chlorinated solvent plumes were ISCO, and the chrome plumes were the ISCRA using 3DME and the sodium lactate. But even with the 3DME and the sodium lactate, we have seen reductions we had very low concentrations of chlorinated solvents, but we have seen significant reductions in those areas as well.
Okay, so I think maybe this question was answered by your response to the last one. Not sure if you have anything else to add. I'll just throw it out there for you. The question is, why was ISCO selected over in situ anaerobic remediation to treat the chlorinated VOCs?
Why we're using ISCO instead of bio, I think.
Well, the bio, again, we were looking at abiotic degradation that was going on. We had heterotrophic plate counts that were, less than 1,000. And we also had other factors like the nitrates and the sulfates within the formation that we would have to overcome. So I think it made more sense just to look at oxidation as a destructive tool for the chlorinated solvents.
Okay, next question is, what is a drop stone?
Well, from a geologist, thank you for that question. A drop stone is, consider you have 1 mile of ice over the northeast, and that meltwater is receding, and you have an iceberg sitting within Glacial Lake Hitchcock. As that iceberg melts, you have a conglomeration of sands, silts, stones, boulders within that iceberg. As that ice melts, those stones will then drop within that glacial lake. In this particular case, that drop stone dropped within the clay unit, or what is referred to on this side as the lacustrine deposit, and embedded itself within those lake bottom deposits. So it's really a stone from the iceberg to the bottom of the lake.
All right. Next question is, did you see any effects of desorption of CVOCs from the silts and clays back into the sandy units following treatment? And what did you observe with TCE daughter products, i.e. vinyl chloride, and dichloroethylene? Okay,
on the latter, we did not see the vinyl chloride or the DCE as a result of the oxidation. On the desorption side of things, in the areas where we had predominantly chlorinated solvents within the more permeable units, we saw little to any rebound of the chlorinated solvents. In the areas where we saw the silts and the clays, we did see some desorption, but not as much as we had anticipated. However, we are still working on a zone where there was an area of higher concentrations within silts and clays that we had to go back in and re-inject to address that mass. But again, the mass was much lower. If we look at mass concentrations, the mass inside a 9,000 ppb mass within the fine sands or the more permeable units is much more significant than a 9,000 parts per billion in silts or clays. So we're still going back in and looking at those silts and clays, but we really didn't see any rebound or back diffusion within the more permeable units.
All right, let's see here. Next question is, can you explain drive and wash? I haven't heard this phrase before.
Okay, sometimes they're referred to as drive and wash or wash and drive, but basically what you're doing is you're pounding a casing. You're basically flushing the inside of the casing out with the material that you drove through. You advance a core barrel ahead, and then you repeat. So it's basically just a technique of advancing a boring to depth. Unfortunately, those take days instead of weeks, instead of hours to get down to 90 feet.
All right, let's see here. Next question is, what was the oxidant used during ISCO?
We use both persulfox in the core or the high concentrations, and we use the Regenox in the down gradient core of the plume to treat the chlorinated solvents. And neither one of those did we see any significant rebound or the production of vinyl chloride or DCE.
I have to say, someone made a comment about there's no R in wash. Anyway, that's for us Boston people. Sorry, go Red Sox.
All right. All right, so we have maybe time for one more here. Question is, what are the hydrostatic groundwater levels for the wells?
They vary across the site. The water table wells are anywhere from 15 to 20 feet below grade at the recharge zone. Hydrostatic levels at the discharge areas are 5 to 8 feet below grade. But what's more interesting is that as you go down through and putting in nested wells, we can see very significant downward vertical flow within the recharge zones, such that we actually get to points where in the water table we can use a peristolic pump because we're generally less than 22 feet below grade and we can pull up our groundwater sample. But in the deeper portion of the wells, we can get groundwater levels at 25 to 30 feet below grade, and we have to use bladder pumps to sample the wells.
Okay, great. Thank you so much, Rich and Maureen. That's going to be the end of our chat questions. If we did not get your question, someone will make an effort to follow up with you. If you'd like more information about environmental consulting services from GZA, please visit gza.com. If you'd like assistance with a remediation solution from Regenesis, please visit regenesis.com to find your local technical representative, and they'll be happy to speak with you. Thanks again to Rich Desrosiers and Maureen Dooley, and thanks to everyone who could join us. Have a great day.
Thank you.